speaker is coming from the Quality of Life Center. Go ahead and come up, announce your name in the center. And I understand there's a couple of substitutions, so I'll prompt you by calling your name. So the first one, Quality of Life, Takeo Kanata. Oh, I'm sorry. The substitute for, this is one I didn't know about, sorry.
Okay. I'm Dan Swarek, and I'm from the Quality of Life Technology Center, which is a joint center from Carnegie Mellon University and University of Pittsburgh. And our mission is at the bottom of the slide there, is to provide technology to enable people with disability and elderly to live independently longer. And if we could postpone the movement of people into the nursing home by 1 month, we could actually save over $1 billion a year. So our technology is to bridge the gap between people's intent and their capability. And the way we do this is we have 4 test beds. We have health and wellness in the community, in the home. We also have safe driving to keep you driving longer. We have also mobility and manipulation for people who are using robots both in the home and portable as they drive around wheelchairs. And then virtual coaches, which provide information and advice to people that need cognitive and other types of assistance. And we have 4 basic research thrusts, one in mobility and manipulation, another in perception and awareness, where we use vision and sensors. Then we also have one in person in society, which is trying to see if people will accept the technology and use that to promote their, people will pay for it and people will also accept it. And then we also have human interaction with the technology so that people will accept the technology. And we deploy this to individuals in the community and in society. We also have a number of companies, startup companies, as well as more established companies. And as outreach, we also are an REU center, but we also have something called TechLink, which builds Lego robots, people with minorities in challenging tasks with the robots. And our impact slide is Qualt Foundry, where we actually go through and sift through the actual technologies that the students develop, the test beds develop. Maybe it's a part of a test bed, not a whole test bed, that is then vetted to see if it's got a potential market. Teams of law students and business students look at developing the business plan, secure the IP that's presented to our industrial advisory board for further vetting, and spins out companies. And these are some of the companies. One of the ones, for example, is First Person Vision, which is meant to be the platform for cognitive assistance using vision and also eye tracking. And as is usual, the first customers for this are not the ones envisioned by the researchers. Thank you.
I'm Tom Daniel. I'm here for Yoki Matsuoka. I'm the Deputy Director of the Center for Sensory Motor Neural Engineering. As you can see by the timer, we're a first-year center. So let me give you the big strategic vision first, and then how we went about forming it, and then some research examples and our educational mission. So our highest level mission is to develop adaptive, closed-loop interaction between humans and neural systems in sensory motor systems. That is, things that can both sense and move in response to sensation. And the other byline with our center is that we are really interested in devices that are inspired by and interact with natural systems and neural systems. We formed a partnership with MIT after a history of collaboration in electrode development and now smart skin development, with San Diego State University, with a history of expertise in wireless devices, University of Washington with its emphasis on computing and analysis, and also with our historic collaborations with Morehouse and Spelman College, as well as now a new collaboration with Southwestern College for recruiting underrepresented students to our center. Finally, we have two and now a third international partner. The two international partners are University of Tokyo with expertise in robotics and particularly human-robot interactions. And the second is the University of British Columbia, which has an intriguing addition to us, which is expertise in the domain of neural ethics. That is the identity of people with assistive devices, how they are perceived and how they perceive themselves, and how we examine human value with human-machine interfaces. Our third international partner just stepping up is the University of Freiburg. And they are putting in for a cluster of excellence, which to our reading looks exactly like an ERC. They are required to have an international partner. We are glad to be it. And they are doing a very, very similar thing. It's called Brain Links and Brain Tools. So there are three goals of the center, and I will tell you what are three goals and three examples, okay? So we want to integrate neuroscience and computing to interact seamlessly with people. This is a challenge because current interactions are a bit cumbersome. It also requires interactions between neuroscientists and engineers fairly substantively, and also between that community and industry as well as education. We also need to be able to manage and analyze data, massive data coming from hundreds of channels of electrodes, and infer intent from these data, as you'll see in a minute. And we also are interested in developing devices that actually operate somewhat like neural systems, that is, use multimodal information in regulating their positions and movement in space. One example is being developed by Brian Otis at the University of Washington in collaboration with colleagues at San Diego State. That's wireless chips that can be embedded subdurally or at least subcutaneously, very tiny, low power, low mass. And some of these were developed for use actually in insect systems, so they're very tiny and very low mass. A second area is in decision-making based on analyzing the data that you can extract from wearable devices. So a cap of high-density electrodes that can detect EEG patterns, electroencephalographic patterns. If you can determine intent and motor cortex activity, you can control small robotic devices, such as the little gizmo right in the middle of the slide, which is a small robot that you can steer around through cortical thinking. And finally, low-power wireless ECOG, that's electrocorticography. And it's not low power, but it's wireless. And right there you have a wired ECOG on a brain in the lower left of that. And this is a subdural array of electrodes from which you can mine data. And at the demonstration table, I would like to show you a movie of somebody controlling a robotic arm using that ECOG array, okay? Our educational goals, we want to encourage students to enter this center and engineering from diverse backgrounds to pursue this career. And to put some teeth behind this, we've actually done two strategic partnerships. One is a strategic partnership with the MESA program in Washington Mesa, San Diego Mesa, California Mesa, and also Mesa in Boston. So the MESA programs are linked through each of these institutions to help move students from their connections into the center at each of our partner institutions. Secondly, we've also collaborated with a DO-IT program, this Disabilities, Opportunities, Internetworking and Technology program, which are students with disabilities, to actually not serve as subjects but as collaborators in this, because they have a passion for pursuit of research in this. Finally, on this encouraging students from diverse backgrounds, partnering with neuroscience is a beautiful avenue for recruiting women into engineering. Currently, our undergraduate neuroscience major is over 50% female, and we're hoping to convince them to move a little laterally into engineering domains and biomedical engineering. We want to provide multiple opportunities for students and teachers to become involved in research and education. And in our first couple months, we have submitted our first REU site and our RET grants. So those are off and running. We've also partnered with a middle school. It's an all-girls middle school. And Lynn Preston referred to something called the Challenge Basin. There's a challenge basin in education. It's called Girls in Middle School Science. And that is the challenge basin to move these students so you don't lose them at that age. So we view middle school girls as a wonderful zone to work to keep people interested in engineering. So that's the challenge basin in our education. Finally, we want to develop, disseminate, and evaluate formal and informal educational programs from pre-college via MESA to undergraduate and graduate curricula. We're developing a certificate program there. And we're also developing an interesting deployable technology to schools that's affordable. It still has live material with live neurons that you can deploy without IACUC or IRB. And it's cockroach legs whose sensory neurons can run small little robots. So, and I think the students really get excited about it. It's very deployable, very affordable, can be mass produced, and the curriculum can go from school to school. And on that note, in the 8 seconds remaining, I'll encourage you to please come and visit our table.
Ready?
Right.
Which one?
This is the pointer.
Okay. Okay, start here. Okay. Okay. My name is Jack Sankar. I'm representing the Revolutionizing Metallic Biomaterials Center, ERC, from North Carolina A&T State University. You're playing basketball. You think you can out-rebound somebody. Take the ball, you're landing. Land on somebody's foot, break your ankle. You're running. On the curve, you break your knee with the ACL joint broken. All the time we hear people sleeping in the bathroom, could be a relative, joint is broken. The baby boomers are growing, heart problem, stent is put. So obviously one of the problem is the implant the doctors put remains inside. There are a lot of multiplication. The question is, we do better than that? That is one end of the spectrum. Other side of the spectrum, you got babies born with cleft lip, congenital heart problem, the stent has to be put. Accidents, car accidents, falling down, head broken. So now the doctors puts implants with multiple screws. The kid is going to grow. He's going to become a boy or a girl, taller, but you have to do multiple surgery. So the question is, can we do something to replace this titanium and the stainless steel implant? Yes. That's why we want to do revolutionizing that idea, not the evolutionary. This is almost like Steve Austin. Ladies and gentlemen, we can do it better. We can make it smarter. And we will develop the technology. The question is, they asked me, what is the home run slide? I thought about it. So many things we do. But I have to come up with a slide that means, which cuts across the area. So that's our second slide. Okay. If you look at this is our strategic vision. The bottom gray area is the design parameters where we are going. This is like Google telling the direction where you want to go. So this is between the CSAB and the IAB and the doctors and the ERC team tell these are the parameters you need to reach. Then the scientists across the university of our ERC team, there is a red team, works on innovative materials, revolutionizing the idea in magnesium, which body needs, is biodegradable. Then the blue team comes and works and do all the characteristics. Then the green team, like Greenberg told, it's in the green. So that's what the biocompatibility goes in the human body. So it takes the animal into the clinical trial. This is for the ACL, one thing. So all the devices, we have this strategic plan. But on the left side, as we are going, we are giving a trail of economic development innovation. So that can lead into multiple economic development. While the magically disappearing screw can take 10 years, but we can do economic development every down the way. But below this, if you travel, everything has got education outreach. So every line behind the courses and the REU and RET is there. So that's my home run slide. Thank you.
Okay, thank you.
Good afternoon, everyone. I'm here on behalf of Dr. Mark Humayun. I'm Jim Weiland. I'm the Deputy Director for the Biomimetic Microelectronic System Center. And the problem we're trying to solve is shown on the top, that the human nervous system, when it is damaged, does not heal well, if it heals at all. And this is something that's is fairly well known. Our goal then is to develop the biomimetic microelectronic systems that will form direct high-density interfaces with the human central nervous system to restore this lost function. You see our two test beds depicted in the center. On your left is the retinal prosthesis. So this directly interfaces with the retina of a blind person in order to restore the sense of vision and give them some partial sight. In the center, you see a direct brain interface. The test bed that Dr. Ted Berger is developing is an interface with the hippocampus, and that has a role in memory and learning. And what he's shown in research in an animal model of memory loss is that Ted's really great at putting things concisely. In Ted's words, paraphrasing, but very close, if you throw the switch, they remember. If you turn the switch off, they forget. And if you turn the switch on again, they remember. So there's more details in his journal article, but that's the basic essence of it. So it's really been a remarkable breakthrough that he's had fairly recently in his test bed. In terms of our major impact of our ERC and for the retinal prosthesis, the Argus 2 retinal prosthesis is a commercial retinal prosthesis, the first ever in the world that was sold recently for the first time in Italy. What we've been able to show with this is improved mobility and reading of large letters for people who are otherwise completely blind. At our table, I'll show some videos. In the ERC, with novel biomimetic technology and improved scientific understanding, we think that will lead to better clinical outcomes. And you really need both. What I'm showing right now is a biomimetic electrode array developed by Y.C. Tai at Caltech. And it's biomimetic because, as you can see, it not only has a large number of pixels versus the array, the Argus 2 array, they're arranged in a biomimetic format. There's a variable density of those electrodes on the retina, and that density matches the retinal ganglion cell. So understanding the biology to which you're trying to interface, we think, is very important. But it's not enough just to make the technology. We also need to understand how it's used. And I'm sure no one can guess what that is, so I need to tell you for sure what that is. And that's a retina that is changing its fluorescence due to intracellular calcium. And it only changes its fluorescence because we actually genetically modified that retina using viral vector techniques so that it would do that. And because of that, it now allows us to interrogate the retina and understand its response to electrical stimulation that much better. Our contention is that by making these, following these biomimetic design principles, we can go to this resolution to this resolution. And I'm clicking the button, so.
Let's try.
Oh, wait, it's going now. Okay. In terms of education, Joe Kokoza did an excellent job presenting this morning. I'll just add the impact of having a student in my lab say that she had no idea what engineering was until she came to the EHA, and now she's an engineering freshman at UCI. And the light is blinking red, so that just shows our cumulative impact in terms of output, and that's just very attractive to industry. Thank you.
Hi, my name is Nasser Pegambarian, representing Cyan. Slide before that.
Oh, that goes backwards.
This one. Okay. Cyan, or Center for Integrated Access Network, includes University of Arizona, UC San Diego, Columbia University, USC, Berkeley, NSU, UCLA, Tuskegee, and Caltech. Our goal is to transform internet to a high-speed web that is scalable, that is low cost, affordable, and also doesn't use that much energy. And so we are focusing on trying to take care of the bottlenecks and challenges that the current internet has. One of those challenges, for example, is that even though there are terabits of information running through the fiber network connecting different cities, by the time you're trying to use it at home or at the office, only a trickle of that comes to you at a couple of megabits per second. That's part of the access aggregation network that we're looking at. That data centers is another challenge and bottleneck, where anytime that you want to use Google or you want to use your Facebook, you got to go through one of these data centers, And these data centers are all electronic machines. They are very expensive. They're usually built near a source of energy generation. And so what we are trying to do by creating optoelectronic technology, we are trying to make it scalable and trying to get the cost lower and make it fast. So the examples of the research that's going on here, on the left, you're going to see a paper that was published in Nature about telepresence, holographic telepresence that Lynn talked about. But also, if you look at the, that's part of our Trust 1 research. If you look at our Trust 2 research, we're trying to integrate various optics and electronic components on the same chip. Think of an Intel chip that is mainly electronic components on it, transistors, resistors, and so on. Our silicon photonic chips includes not only the optics, not only the electronics, but also optics, all integrated to get the cost low and also the energy consumption lower. A paper on that area is published in Science 2 months ago from our, in fact, that was an interesting story. A student of UCSD went to Caltech, and together they actually came up with this, what is called the optical diode. So that is another example of Trust 2. A third example is from Berkeley. Again, a student from Berkeley published this paper on nano lasers that you can see on the right side. So these are examples of the research that's been going on at Cyan. Thank you.
Okay. So good afternoon. I am Jorge Roca, and I am from the Center for Extreme Ultraviolet Science and Technology. That is a partnership between Colorado State University, the University of Colorado at Boulder, and the University of California, Berkeley, Lawrence Berkeley Lab. And the goal of our center is to extend the benefits of laser light to society. We are all familiar with the benefits that lasers have brought to society, including like laser eye surgery, optical communication, and the printing of the fastest electronic processing chips, and many others. And all of them have come actually from lasers that emit light very close to the visible region of the spectrum, and or a fraction of a micrometer, actually. And if one, I guess we'll hear from Claire about the lasers on much longer wavelengths. Our center focuses on lasers at much shorter wavelength. Let's say lasers which wavelength is, let's say, 1/10 to 1/1000 of the wavelength of visible light. If one can make practical lasers in that region, right, one is on the range of dimensions, which is of interest for nanotechnology. And actually, a few nations have recognized that. On the last 10 years, they have invested hundreds of millions of dollars on, oh, it's the wrong slide. Okay. They have invested hundreds of millions of dollars in facilities that you can see here on the bottom left, so-called free electron lasers, which are basically accelerator-based facilities, which cost up to $500 million. They are hundreds of meters in length, right? They emit intense laser light in the extreme ultraviolet and soft X-rays. What we propose is to develop very compact lasers in this wavelength that fit on a table and or on a small desktop, such that instead of having to take your application instead of having to take the application to the source, you can take the source to the application. And in terms of In terms of an outcome from this work, we have succeeded in developing these compact table sources. They are tabletop sources. They are commercially available, and they are making possible the development of instruments that are very compact microscopes, printing stations for printing devices into the nanoscale, new probes onto the nanoscale, a set of new tools for nanotechnology. And the other major part of the output is our center graduates. Now we are in year 9. There is many students that have graduated, and all of them are receiving multiple jobs from offers from industry, and they are really making a major impact in industry. Thank you.
Let me reboot this so that you don't run out of, okay, yeah, that's a laser pointer. There you go.
I'm Claire Gmachli. I'm the director of MIRTH. That's a 6-partner university center on mid-infrared technologies for health and the environment. Our partners are City College New York, Princeton University, University of Maryland, Baltimore County, Johns Hopkins University, Texas A&M, and Rice University. And we develop the next generation trace gas sensing systems. If you think about the air you're breathing in, and you hope it's healthy, if you think of the breath you're breathing out and you think it's healthy too and smelling well, we know. We can measure parts per billion of trace chemicals. The applications that we focus on are urban air quality sensing, air pollution, sensing for climate research and climate change, health, breath analysis, and applications in security. And why does the technology work? Because we work with one of the strongest light-matter interactions that there are. We excite the fundamental vibrations that molecules have with mid-infrared light. And it's a winning technology because what we use for that, quantum cascade lasers, mid-infrared lasers, and then electronics and the internet and smart stuff, it's already been out there in the infrastructure in the telecom industry. So we're using fundamentally one of the strongest foundations that there are in light-matter interaction and an infrastructure that has a lot of experience and history with it. When we started as a center, what we do was a lab curiosity, good for papers, good for academic research. Now we bring our work into the field, being part of real air quality studies that provide data for communities. We bring them across the globe into highly resource-constrained environments. And what used to fit on breadboards and optical tables, now you can fit in the palm of your hand. When we started in the US, there was no commercial outlet for the devices, the systems, the applications that we are working with. Now you have many. Let me also, go with the education, tell you a little bit about our education philosophy. We want our students to be trained, to be knowledgeable about important problems. Which are the problems to tackle? And once they know which problems are good ones to work on, we want them to be trained superbly as engineers to solve them. They are part of a workforce that is diverse, global, collaborative. And they are leaders. And I think you met several of them already. Lone told you about the student-led projects in MIRTH, and I think she made a case to the NSF that they should just give the money right to the students. And you met already one of our wonderful examples of students who were grad students and now are entrepreneurs, Yan Zhang this morning and Stephen So tomorrow. And I want to thank with a thanks to the NSF making this possible and a thanks to my students, staff, and faculty. Thank you.
Just reset that. That's the pointer.
Okay, good afternoon. I'm Dave McLaughlin with the CASA Center. My partners are University of Oklahoma, Colorado State University, University of Puerto Rico, Mayagüez, and University of Massachusetts. We're trying to create a new technology that will enable a better response to hazardous weather events like tornadoes, flash floods, landfalling hurricanes, and things like that. Now, this past year was an awful year for tornadoes. You've been hearing about it in the news. hundreds of fatalities, billions of dollars in damage associated with weather events. In one particular tornado, in fact, we heard about another one at lunch yesterday, but in Joplin, Missouri, in a community of 50,000 people, there was one twister that killed 150 people and injured about 1,000 people. The assessment that came out from the National Weather Service said it was basically a successfully warned event. But you had all that consequence because of a failure in response. It's people just don't know what to do when they're under warning. 80% of our warnings are false alarms. So what we need is a system that provides geographically specific, actionable information that the public trusts and can respond to appropriately. And that's what we're trying to create in the CASA project. So look in the top left of the slide up there, you see the problem. The infrastructure that we have today is a network of very big, high-power, expensive Doppler radars deployed across the country. Because they're so far apart, this was built, by the way, in 1988, pre-internet. Because the Earth is curved, they can't see close to the ground. They just can't see the weather that impacts us where we live. And so forecasting and warning is based on looking aloft, feeding that data into models that basically extrapolate, try to make the best guess about what's going to happen at the ground where we live. That's the fundamental limitation in the quality of our warnings. So the system that we're building is shown in the lower right. It's a more modern internet take on things. We want to solve that Earth curvature problem with lots of small radars, lots of them deployed on cell towers, rooftops, and other elements of the infrastructure, and wire that up like an information system to give people the data they need and can respond to appropriately. The two home runs I want to talk to you about are both associated with our test beds. Hallmarks of the CASA project have been system-level test beds. System-level means it's hardware and software deployed out there with real weather and real users. On the left side, you see our grown-up system out in Tornado Alley, Oklahoma. And that's a system that we deployed. It's 4 radars, about 1,000 lines of code. And you can see the quote from a user. That's from Nick Nazar, who's a community manager in Newcastle, Oklahoma. He's sort of like Steve Hewitt, who spoke to us at lunch yesterday. There was a tornado out on the ground that was zigzagging faster than the big national system could keep up with. He used that system to deploy, to do evacuations, to close shelters, and deploy first responders, and he believes that that saved lives. That's validation for you. On the right side, you see our student-led test bed. About 10 years ago, what we decided to do in CASA as a way of sparking a sort of a systems perspective in students is give our students complete ownership of a test bed. And they've brought us to a completely different part of the design space. They've already been out supporting Central American games. They've developed their concept of an off-the-grid test bed, and now they've launched a company, and they're ready to go out and sell that thing to the world. Thank you.
Wow. Okay, I have to say, after the whirlwind this morning with the elevator pitches, and then I come to see the pros do it again, I think this has been a great day. Thank you very much. Please take advantage of the fact that these presenters are going to be at tables outside, and you can go and collect more information while we scan.